think we're streaming. Let me check real quick. Right, I think we're streaming. Let me check real quick. I mean, it sounds pretty decent. Quality's a little bad, but I think it's because I'm just shuffling around a bit. Alright, yeah, I'm gonna pop this chat out and get it started. Gotta hurry up because competition's tomorrow. I don't want to go to bed too late. Yeah, that looks good. Let's open up that tab one more time. Share this URL around a little bit. Put this here. Put this in here. Maybe like all right. Oh, one more thing. I'll post that on my story. So let's go over to Instagram. And put the link. Done. And my stories. All right, post everywhere. Let's get to it. So we have our final puzzle, which is the quantized matrix mult. When doing matrix multiplication with quantized neural networks, common strategy is to store the weight matrix in lower precision with a shift and scale term. For this problem, our weights will be stored in 4 bits. We can store FP int of these in a 32-bit integer. In addition, for every group of weights in order, we will store 1 scale float value and 1 shift 4-bit value. We store these for the column of weight. Excuse me. Not sure what that means. The activations are stored separately in standard floats. Mathematically, it looks like this shit. I'm not reading on that right now. However, it is a bit more complex since we need to also extract the 4-bit values into floats to begin with. So we have this visual, we have our input. So I looked into what quantization is a bit and how it works and all that, because these problem descriptions are vague enough that it was insufficient for me, right? Here's the rundown basically, right? I'm gonna make a new board over here. So the rundown is when we have several numbers in a line, and say these are all just weights on our number line, so maybe this is 0, right? So this might be like minus 30 or whatever, right? I'm not gonna write it all out. If these are all stored in FP32, that means each of them take 32 bits to store. And if we want to shrink it, so we only need 4 bits for each weight, we need to find a way to represent this initial distribution of weights in a compressed format. And so the way we might do it is we might say, all right, let's try to shrink. try to map every one of these to an integer between -8 and 7, right? So this might be -8, and then we have 1, 2, 3, 4, 5, 6, 7, 8. I don't know. I'm not counting. This might not be correct. Let's just say this is 7. We might try to do a best faith like shrinkage onto here. We might say, all right, here's this one goes here, this one goes here, this one might go here, this one might go here, this one might go here, and this one might go here. And the way that we would determine which one goes where, right, is by sort of just, there's several different ways you could do it. There's linear quantization, there's symmetric, there's group symmetric, group linear. The point is that for the most part, we're going to try and find a way to keep the ends of the range similar. So maybe we will find a min and a max, and we'll treat those as the -8 and the 7. Or we might just find that the largest distance from 0 and make that sort of our bounds. And then we will linearly interpolate to the best spot on this number line and kind of round up or down as needed. So we will lose some fidelity, some granularity, right? Because there's way more intermediate values in FP32 than there are for like less and less bits. So if there's more bits, say if we had 8 bits, then we might have, what's 2 to the 8? 256, right? So we might have -127 to 128. There's a lot more little slots, and we'll have a better faith interpolation. But in this case, since we only have 4, we only get these slots. Now, the key thing to notice here is, like, let's look at our example. So for our scale, we have 32 by 8, because that's our group, right? For our weight, we have 32 by 8. But then for our offset, we only have 32. It's like, where's the 8, right? What they told us was that each 32-bit integer has 4-bit values in it for the group weights, right? So what we notice is that if we kind of decompose this into how would I say this, like 4 times 8, we see that goes to 32, and so we actually have 8 values here as well. It's just that instead of 32-bit values, they're 4-bit values, right? Well, actually, I'm saying this wrong. This is the size of the tensor, right? We should be looking at the data types right here. Right, so like this is a 32 by 8 of 32 values. So if we have 32 by 8 of 32, and here we have a 32 of 32, and here we have a 32 by 8 of 32. But what I'm trying to get at is for this, excuse me, for what I'm trying to get at for this is that this is more like we have 32 of eight times 4, right? And the way that we extract is by unpacking, right? So if we just think of literally like, I don't know, how would I write this? If we just think of, we have several bits all together. I don't know how many this is. We kind of take it apart in chunks and then interpret each of these as an individual number, right? So I might take this chunk, and then I might take this chunk, and I'll interpret each of these as my offset. And for a 32-bit value, there we can get 8 of these chunks for each 4 bits, right? And that's sort of what's happening here. We have this mask. What is 2 to the 4 minus 1? That's 15, right? What's 15 in binary? It's literally just going to be, So they're just going to be this, right? We have 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. And then we're sliding this over each piece. So like we're looking at this 1, 1, 1, right? And we're just grabbing 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? We're grabbing each of these chunks and treating them as an individual number, even though this is how we're storing our int32. And by the way, the reason we're not doing any math on these int30, the reason we're having to do it like this is because the Google Colab hardware doesn't actually allow for us to do certain operations on 4-bit ints, right? Essentially what we need to keep in mind is that the hardware we're using is specialized for the hardware we're using is specialized for floating point operations, which satisfy certain format when they're stored in memory. And so like our ALUs and all this, they might not actually support some of the operations we'd want to do with int like 4 or int 8 and so on. So we have to pack it in and pull it out. So first order of business is like this is matrix mult. We already solved the matrix mult, so let's just copy our old code over, right? One thing you're going to notice is that this is a 3-thread program, and this is a 2-thread program. You might go, oh no, right? But the thing to notice here is that we don't have a batch dimension, right? We just have matrix activation. We want to get our result, right? Without having to store the entire matrix in memory, we're going to store a quantized version of it, and we're going to dequantize on the fly and calculate our result with much less memory, right? So what we can do to accommodate that is just get rid of our batch dimension, right? Let's get rid of this batch offsets, get rid of this batch mask, get rid of this, right? Get rid of this, get rid of this, get rid of this. All that. And I might have to rethink a little bit of this, right? Like, like this should look a little different now as well, right? This doesn't have 3 dimensions, it has 2 dimensions. So let's make this, let's shrink this back down to 2, right? How do we do that? I think we just go like this, right? Like that. Get rid of this batch dimension for both of them, like that. And so now one more thing is now we don't have what we used to have, right? So this has sort of been accommodated to not have a batch dimension, but what we didn't accommodate for is that we don't have x and y now, right? We have our z pointer, we still have our n0, n1, and our mid, our b mid, b1. So all of this is going to kind of still work the same, right? But what we didn't take into account is that we're missing our x pointer and our y pointer, right? You notice that? What we have now is our scale pointer, our offset pointer, our wait pointer and activation pointer. So our activation is actually what we want to our activation is actually what we want to multiply by now. So our activation is essentially our y now, right? So I might just write that explicitly, right? I might just say y pointer equals activation pointer because I don't want to rewrite everything. But then, or actually, hold on. X times y. Yeah, at activation times y. The thing is now, to get our x, we essentially need to build it up from our quantized weights right here, and our quantized weights, and our scale and our offset, right? So this is going to be our hard part, but let's get to it. Let's give it a shot. One thing I'm not clear on is like the group semantics is a little confusing to me right now. Like it's not clear how group plays into this quite yet. To me, quite yet. But basically, what I think I should be doing is for each, if we remember our sort of logic from the last one, each time I have my block that I'm considering, I should be let's see. I should be only like unloading the weights I actually need, right? So this part makes sense to me. But here, for x offsets, it's going to look a little different. Everything here for the x is going to look a little different. Now to get our x, what we need to do is gonna have to be to build it up from scratch. So I'm gonna do the logic separately. All of this, I'm gonna go like that. Go like that. Gonna go like that. X X X X X X. Everything. So I think y can stay the same, right? This is basically just us saying, grab the piece of the activation that we need. The activation is stored normally. Not much else to look at there, right? X, on the other hand, we need to build up from our dequantized values. So the way we're going to go about that is, first we're going to determine which columns are relevant and how to grab them, right? So I think this is how we would determine which columns are relevant. But then how do we actually can write in comments what I want to do, right? I want to load in necessary offsets. I want to load in the necessary scales. Load in the quantized weights, necessary quantized weights, dequantize this is our X block. And then we can proceed, right? So first order of business, well, these don't have any particular order. The first thing that might make sense is just look at how do we load in the necessary quantized weights, right? The group thing is throwing me a little bit because they really don't explain it. For every group weight in order, we will store one scale float value, one shift 4-bit value. Okay. So for every 8 weights, we will store one scale value, one shift value. And we store these for the column of the weight. So what is 32 here? Okay, so what we need to remember from matrix multiplication, right, is that the middle, this needs to be the same. So here we have an output of 32, 32. Like if we try to map these to the values that are existing there, I'm not sure what's supposed to be here, right? But then we have at 64 by 32, and these are real floats, equals 32 by 32, and these are also real floats, which means that this has to be a 64, and this could be whatever. It's probably 32. But if we look, we actually only have 8 here. So really what we have here is 32 of 8 times 8 equals a 32 by 64. It's probably a better way to describe it, right? All right, I see. So to determine our slice, we need to treat this as though it's actually 4 times as big, right? So like when we're looking at our x column offsets, let's say we want column 0 through, excuse me, 0 through 12, we need to think about, these aren't the real columns, these are the columns of the dequantized weights, right? So we need to map it back to the quantized weights. Let's see. So what would the quantized version be? Well, anything 8 or less, we want to anything 8 or less, we want to map to 0. Anything less than 8, we want to map to 0. Basically, we want to divide it by 8, right? So we want to say x call offsets we want to say maybe like this. I'm not sure if cdiv actually can accept. I'm not sure if it can accept a tensor. I think it's just for quantities, and we would actually just use the B2 is not defined. What? Oh. Like that. X pointer is not defined. Oh, right here. So you have 0, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, but we don't want this. What if I just said this? What if I just said that work? Yes, this is what we want. So now 1, 2, 3, 4, 5, 6, 7, 8. We're grabbing our first 8 values from the first quantized int, which makes sense so far, right? So a better name for x call offsets quantized would be, this is our weight offsets, right? So now we can load in our necessary quantized weights by doing a tl.load on our weight pointer. Oh my gosh, come on. Plus our weight offsets. And we should probably make a weight mask as well, right? So our weight offsets should never exceed the length of weight, which would just be 8. But where's that 8 coming from? 8 has to be coming from somewhere, right? No, come on. Yeah. Weight offsets is less than mid over group. Okay, but a weight mask here. And this is going to be our weight. Oh my gosh, this is going to be quantized. Weight equals this, right? And let's just print these, see what comes out. Here we go. And then, there is something kind of messing with me a little bit here, which is that, what is the type of this, right? Nah, come on. So these are int 64. It's a little strange. Shouldn't they be int 32? Is there a D-type argument that goes in here? I don't know. Just give it a shot. Yeah, no. I'm gonna see if I could see the definition for load over here. I don't know what a linter isn't working in Colab. Yeah, we have pointer, mask, other, boundary check, padding option, cache modifier, vector policy, volatile, builder, tensor. Yeah, I think you just have to assume that that's the type. But, okay. I don't like that it's an int 64. That's a little bit confusing. What if I... Is there a way for me to see what the binary looks like? Int object is not iterable. What? Let's look at the shape. It's 1 by 64. Yeah, so can't I just do like... I want to see if I could grab the first integer and see what its bits look like. And what I'm hoping is that it just starts with a bunch of zeros, right? Because then that means we can just treat it like a 32, and we kind of just have to accommodate for a little bit. Otherwise, if it's a 64, I don't really know what to do with it. It's why can't I get this element? What? Am I missing something? Let's get rid of this, right? This is a tensor, right? Okay. Maybe I'm doing something really stupid. I'm gonna ask ChatGPT about this one. Yeah, it looks like I should be able to do that. What's going on there? See if maybe there's something new I need to learn here that I haven't seen before. It kind of looks like that should just be working though. I don't really know what. Everything all right? What happened? int object is not iterable. I'm a little confused because like I know I'm working with addresses, right? But I thought in the interpret mode that it's building up a list, sort of like for my convenience. Yeah, like what is the type of this? It's Triton tensor. I feel like this might be hallucinating. Int object is not it. How about if I said dot flatten? Yeah. What are my methods that I have on TL? TL dot what? Okay, I have a better idea. What we're gonna do here is we're gonna just do the mask, right? We're gonna do the mask, and then we're just gonna look at the values of the mask for each part of the integer and see if it makes sense or not, right? If it starts with a bunch of zeros when we mask it, then my hypothesis was correct, right? Let me say mask equals 2 to the group minus 1. No, That's not what we want. We just want this. Mass goes 2 to the 4 minus 1. That should probably happen like way up here, right? Just like this. And then we want to look at this, right? So we want to say our dequantized weights. Not quite. We want to say our quantized weights equals quantized weights mask, and we need something that tells you how much to shift over, right? So basically what we want, if we look back at this, right, we want this to have the first 4 bits, and then the second 4 bits, and then the third 4 bits. We want to do that for each of these, and we want to do that for each of these, and so on. So basically what we need is to just have we need something that looks like we need over equals tell that a range 0 to we need this a range 8 times 4. And then we need to duplicate this however many times we're going to do extract, right? Unless we do it a bit differently, I don't know. Oh, I think if we just wanted to repeat like that, it'll broadcast. That makes sense. Yep. So end. Oh, yeah, let's make this a 0, like that. $64 and 8. Let's print quantized weights dot shape over that shape. 164 and 8. maybe let's get rid of this. And then let's try that. Aha. 9, 8, 0, 11, 15, 15, 15, 15. And what if instead of 8, I put a 16 here? No, come on. I need it all to come out. Is there really not a way to see? Okay, 15, 15, 15. 1, 1, 1, 1, 1, 1, 1, 1, 1. Oh, let's look at the last ones. Like this. 0, 15, 50, 50, 15. 0, 0, 0, 0. 15, 50, 15. 0, 0, 15, 15. See, something's wrong here. Something's like kind of funky. I'm just gonna assume this is the correct part. And the reason is because I want it to be. We're just gonna hope. We're gonna go off hopes and dreams, right? Let's see. I'm gonna call this packed weights, right? And let's print the what is happening? Okay, 64 by 8. Is that what I want? And then now that I have each of these, I want to take the diagonal, right? Come on. I think you're just tired, Jay. All right. I might mess with this a little bit myself in Python, right? Let's go over here. We gon' yeah, look, it's all ones. It's all ones. 1 1 0 1 1 1 1. How about this? How about this? I think we should just be ignoring all of these. It's kind of cursed that it's not written to the like it's not always zeros, but I think it's fine then, right? Just always have this at 0, 8. Yeah. All right. But then, how do I actually get the number out, right? Ask how I can do this shift better. I think I'm doing the broadcast wrong, but I haven't done a lot of broadcast logic with vectors. Let's see. Say yeah. I see. So what I want is this. like that. Maybe. I don't know if you can index like that, but we'll give it a shot. I haven't encountered having to do operations like this in Triton. This is throwing me a little bit. I'm glad I practiced this before the competition. Can't go too much longer though. So I might have to do a part 2. Basically what we want is to map each of these to the correct part of their bit representation over here. And it's just not clear to me how, because we can't use normal Python constructs. Let's look it up. Triton bit. See if maybe there's a code snippet
Yeah,
in
so
here that has like a pack 4-bit. They are using the modulus, but then Oh, there's no way there's a built-in. There's no way. Okay. Yeah. I would say like. Unpack mask. Already have that. Well, really, I just need a repeating vector, right? Like, So I think instead of doing this, what I should do is I should say, let's make this a B mid, right? And then we can make this a mod group times 4, like that. Let's try that out. And then over here, we don't have to do any of this weirdness, right? That just shouldn't be happening. Like, let's try printing. Let's print over. That looks right. Here we go. I think this is what we wanted. And mask. So this is our quantized weights. I think we could do the same for the other values as well, right? So let's try this for the offsets and the scales. So our weights were in 32s, our offsets were also in 32s. This time, our offsets are for each group. So I'm gonna call offset shift because I like it better. And then we're gonna call these shift offsets, right? Call this the shift pointer. Call this the shift. call this the shift mask. Packed shifts. Quantized shifts. Except that part's not quantized, really. So we should probably just be calling these shifts. Like this. Let's see. See, this isn't quite right. Something's not quite right here. Load in our necessary scales. So for each shift, there should be a corresponding scale, but they might apply to a group of weights, not just a single weight, or all of the weights, right? That's where I'm a little confused here. I think really what's happening is that I think what we really want is like the group offsets, right? But let's keep trying it, right? Let's just keep with the copy paste and I'll change it as we go. Except these aren't packed. These are just the scales. This is our scales mask. And then to get our scales, we don't have to do any unpacking. Put our scale mask like that. Okay. Let's look at the shape of each of these. That shape, that shape, that shape. And they're each 64 long. Weight will be stored in 4 bits. We store in addition for every group weights in order, we store 1 scale full value, 1 shift 4-bit value. So weight is 32 by 8. So this should be a 2D read, but I don't 100% understand what's going on with the groups there. We're almost there though, right? Because then now all we need to do is we would find the dequantized weights equals this, right? And then we put the dequantized weights here, right? So what I'm trying to figure out here is like, what is our grouping scheme? So we should still remember what our row is and everything. Okay, I see. So over here for our x offsets, right? For our weight offsets, we should be our packed weight offset should equal this, right? We need to expand it though. So this needs to be none like that. And then this needs to be like that. And instead of mid, we want group. I think. Packed weight offsets. Let's try that. So how do we dequantize the weights? We need to take the quantized weights and do a cast 2 TL.float32. And then we need to subtract the shift and multiply by scale. Like that. Try that out. Okay, we got quantized weights. That shape is 16 by 64. And then shift and scale shape seem wrong. I'm still a little confused on what the scheme is though, right? Like, okay, I should probably look at this a little closer. ZJK equals, that sounds not correct. For J and 0, K and 1, we want to do sum of L of Y, LK. WJL minus shift J L over G. L over G. So we want to grab all the rows, but then we need to do L over G. Am I doing this right? X column offsets none over group. This is L over G. scale. Let's look over here one more time at what we're doing. That actually probably is probably this is probably the best bet for me to understand, right? My offset. So I'm gonna rename this shift because that's what I did over here, right? Okay, so this extract makes sense. For our scale, we expanded it, right? Don't really see why we wouldn't do the same with the shift, right? But 8 group. Can I say I had to break this down for me because I don't want to play it all out. Yep. Your code to help extract this is by unpacking. Yep. Yep. I see. The group is just for the packed values. I get it now. Oh my gosh. That took me way longer than it should have. Okay, so I just need to make sure that I'm using the same shift for each value. Alright, alright, alright. This shouldn't be grouped. This should be... This should be mid over group, right? So I have my quantized weights. Now over here, what do I want? So what should be happening here is that okay, I see. So for this, we need to kind of have like, when we pull this out, we need it to be like 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, because we're going to reuse the same shift value for every group, right? So I don't know what's going on here. I really don't want to restart it because that'll take forever to run, but might have to. I think we're almost there though. Essentially, like, only thing left is that we need to make sure that we're breaking down the values and pairing them together correctly. But I think we've actually done the extraction portion and everything we need to. Alright, let's see what happened down here. 16, 64, 64, 64. Where's the 16 coming from? Okay. Yep. Yeah. 13, 1, 12, 2, 1, 0, 0. This doesn't seem right. Shift. I think the logic for shift and scale is flipped or something. Something's wrong here, right? One scale for every group of weights. We will store one scale, one shift. That looks right, but what's up with this? Hmm. Oh, this does look right. So for this one, I think it should be 2D, right? This should essentially be like this should be like that, and then like this. (16 by 64). Right. Like that. Let's try that out and see if it's doing what we expect. Okay. So we have 980, so on. Then we have our flow 32 with the shift. Something's wrong here. So we gotta fix that. Okay. So first thing that we need to fix is the shape of shift, right? We need the shape to be we need this to be like a, let's try to see if we can make this a column vector. I think that would make sense, right? So we need to go like this, I think. Let's see if that makes sense. Well, let's do it like that instead. All right. No, it's not what I want. I want each of these to get like I'm gonna assume there's 64 here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 3 is 48 plus 1, 2, 3, 4, 5, 6, 7, 8, 16 is 64. Yep. 9 minus 13 is minus 4. But then how come this isn't 2? Oh. Let's make sure that's also a float 32. I'm surprised it didn't just break. Let's check that out again. Make sure that's coming from the Triton language library. Okay. Yeah, 9 minus 13 is minus 4. 15 minus 13. I see, yeah, it's subtracting it this way. I want it the other way. So maybe there's like a... So I think the issue right now is that I'm subtracting this tensor from the matrix, right? But instead of subtracting each number from each row individually in a sort of like broadcasted fashion the way I wanted to, it's literally just subtracting the row, like the second value from each row, which is not what I want at all. So I think one way I could do this is just by duplicating numbers over and over for each row, but I feel like there's like a better way to do it, right? Maybe not. So it shifts again, right? Like that. Oh, that's not what's happening. I get it now. Well, I don't get it now, but I get why it's breaking. Man, I'm getting really stoned by this. I need to go to sleep soon. If I don't solve this by 3:25, I'm gonna go to sleep. So for each weight, so this should be a 16 by 64, that makes sense. For each weight we want to subtract off We don't want these all to be different. What we want is eight zeros and then eight ones and then 8 twos and so on. How do I do that? I think this should just be TL.A range from 0 to from 0 to B mid, right? And then B mid is 64. Yep. And then we get, do we get what we want from that or no? These should be our row offsets right here. This should be, okay, I get it. Pack shift offsets should be our row offsets. And pack shift math should be row offsets less than row offsets less than, it should just be a row mask, I mean, sorry, row mask. Pack shifts, we're going to do plus pack shift offsets, pack shift mask. Then to get our shifts, now we have the shifts for each row. What we want is this what we want already? Now for our shifts, we have, what do we have? We have 16 by 64. That's not quite how I want it to look, right? There should be repeated values here, and there aren't. But some of these should be true at some point. Let's see. Let's do okay. Packed shifts. What does over look like? This over is wrong. We want this over to be something else. I don't know, I'm just calling it S for now, right? We want this to be 0 to B mid, but instead of modulus F point, we want it to be divided by group, right? And then I'm gonna put an S here and see if that goes how I expected it to. Kind of, except I think it should still be going over by 4, right? Like times 4. Let's do it like that. Hey. Okay, so now I'm going to explain what's happening because I know I didn't explain that very well. There's probably a better way for me to do this. I don't know, what would I... So let's maybe name these over a little better. This is a shift over, and I don't know where I use other over. Come on. Okay, over here. Let's call this the weight over. Sort of some SRAM each time. We don't have to keep recomputing it, right? Okay. So we're gonna run this one more time. Yeah, I bet it's not. Come on. Alright, so we solved the final Triton puzzle. I'm pretty proud of that. How did we do this, right? So we borrowed our MapMul algorithm from the last time. If you didn't watch that, watch previous kernel. I'm not going to re-explain it. This one just doesn't have the batch, but essentially we're looking at tiles of our matrix and accumulating the sums of their dot products into an entry. But it's not just a row and a column. We're treating the matrices as associative elements that we can add together, right? But the key thing here is we treated our y exactly the same, but to be able to get the correct result from our compressed matrix, what we did was we loaded in the proper weights, compressed weights, and we did so by doing some bit math, right? So we know each entry was represented as 4 bits, and each of those 4 bits were all packed together into a 32 in 32. So we said our group size is 8, since 8 packs of 4 fit in 32. And so whenever we are grabbing our weights, we divide it by group to make sure that we grab the correct index, right? So instead of grabbing columns 0, 1, 2, 3, 4, 5, 6, 7, 8, we know all the first 8 elements are in the 0th group. So we divide by 8 and assign all those numbers to 0. Same thing for 9, 10, 11, 12. We know that those would be in the second group, which would have index 1. So 9 divided by 8 without the remainder is 1. 10 divided by 8 without the remainder is 1, right? So that's sort of what this is doing. And then to unpack, we're scooting over, right? We have those packed bits. We're scooting them all the way towards the bottom of the register, right? So we have the part we care about in the ones place, and then we're using our mask to chop off everything else, right? So first we scoot over nothing to get the first one, we mask and we get that chunk, then we shift, so the part that we were just looking at gets discarded, and the next chunk is there, and we mask out the rest. Shift, mask out the rest. Shift, mask out the rest till we extracted everything, and we cast it to float 32, right? I do that down here. I probably could do that earlier, but I don't want to. Same thing with the shifts, right? For the shifts, we just grab the necessary rows, and then we do our bit shift. So it's kind of confusing. This shift is talking about the 0 for this, right? This is talking about where is the 0 compared to where is this 0, right? Since we did a linear interpolation, we need a scale factor and we need a y-intercept. So that's what this shift is versus the shift I'm talking about. I've been referring to as over in the code. And over is telling you how many bits to shift over. Versus shift is telling you how the number line is shifted in the original weights versus the quantized weights. But we do the same thing. We just shift over, right? Each group of 8 gets its own 0 in the number line. That was sort of the scheme here that they gave us. It just took me a while to understand. And then load in necessary scales. We do the same thing, right? But this time we need to do a 2D, just like we did for the weights, because each why do we need to do 2D? Because each scale was a float 32, right? Which means that we actually need to grab 8 from memory. We couldn't just extract the 8 from an int 32. We didn't compress the scales, if you look, right? So this is actually a good way for you to understand the difference between grabbing the numbers directly versus grabbing them from ints. When we grab them directly, we need to use 2D indices, right? This is sort of my row and column vector, and it's going to take up quite a bit more, so I'm going to get rid of this since it's already float 32, right? It should still work. Yep. This is going to take up more space because we basically had to take up 8 times as much space because they weren't compressed into that format, versus when they were compressed, we had 8 times less space, and we used a 1D index, but we had to do a lot of unpacking logic that was a bit hard to think about. And the last thing was dequantization block. Dequantization, this just means we're gonna bring the 0 over to the original and scale it back up to the original size, right? So I subtract my shift to get us back from here to here, and I'd multiply by scale to get our endpoints back to here. And then I'll recover all of my original values as well as I can from the quantization, because the quantization is lossy. Then I just complete the rest of my algorithm, not going to explain that part, and get a result. Nice. I'm going to post this on GitHub and go to sleep because competition is tomorrow. So let's go to 12, puzzle 12. And I saw a note in the I saw a note in the repo that said it wouldn't work when you ran it, so I'm not even gonna bother, right? We're just gonna get rid of this. And let's try running it right. Python. I really don't remember what the command was for this. All tests passed. So let's go git add puzzles.py. Quantized matmul. Git push. And I'm gonna make more polished versions of solutions for each of these puzzles and upload it onto my channel. This was just sort of to show me banging my head against the wall, right? And I hope it was useful to anyone that watched it. Peace out.